Hello everyone. Today we start chapter 2 about the real numbers. The general approach in this chapter is that we start with describing essential properties axioms and then using these axioms we're gonna prove certain theorems, statements, and corollary. So deduce, theorem, and corollary. We start with algebraic and order properties of the real numbers. So these are the algebraic properties and they are called the field axioms. Let R tilde be a set of elements with two binary operations denoted by the following symbols. First, we have this symbol denoting addition and the dot symbol here denoting multiplication. These operations gonna satisfy several properties. The advantage of this approach is that the theory that we are developing only depends on these very fundamental axioms. That's why the theory can be applicable to many situations as long as these axioms are satisfied. So we're going to have several axioms here grouped into the properties of the addition operation and the properties of the multiplication operation. So A1 here is just the commutative property of addition. A plus B equal to B plus A. A2 here is the associative property. A plus B first plus C is equal to A plus B plus C. So on the left hand side here, you take the addition of B and C first and then add it to A. The third axiom here is about the zero element. So there exists a zero element in the set of real numbers such that if you add this zero element to any element in the set of real numbers, then you obtain the same number. So 0 plus A equal to A plus 0 equal to A. The fourth property is that for each element A in the set of real number, there exists an element denoted by minus A also in the set of real numbers such that A plus minus A is equal to the zero element. So these are the axioms about addition. And you notice that here I'm using certain symbol to denote the zero element. So think about it as not just the number zero that you are so familiar with, but a symbol satisfying these properties. Then we're gonna have a group of Asians about multiplication. The first statement here says that A multiplies with B is equal to B multiplies with A. So again, this is just commutative. The second statement is also about the associative property. A multiplied with B multiplied with C in that order equal to A multiplied with the product of B and C. Then the third statement is about the number one element. Again, it is denoted by a special symbol here to emphasize that this is just a symbol satisfying these properties, these agents, and not necessarily the number one that you are so familiar with. And so the number one here satisfies the following properties. First, it's not equal to the zero element. Second, element 1 multiplies with A is equal to element A multiplied with 1 and equal to A. The next axiom here is about the reciprocal. For each element A not equal to the zero element, then there exists an element denoted by 1 over A, also in the set of real numbers, such that A multiplies with this special symbol 1 over A equal to 1 over A multiplies with this special with this element A and equal to 1, the element 1. The final axiom here, as you can see, this is about the interaction between multiplication and addition. So how these two operations interact with each other. It says that A multiplies with the summation of B plus C is equal to A multiplied with B plus A multiplied with C. So these are the algebraic properties that govern the behavior of real numbers. Now we're gonna use these properties, the axiom, to deduce several theorems and corollaries about these real numbers. The first theorem here has several statements. The first statement says that if Z and A here are elements in the set of real numbers such that Z plus A equal to A, then Z must be equal to the zero element. So notice that the zero element here is an element built up in the set of algebraic properties for real numbers. The first statement here, in this sense, can be thought of as a uniqueness property for the zero element. Similarly, the second statement is about the uniqueness property for the one element inside the set of real numbers. For U be inside the set of real numbers, B is not equal to 0, such that U multiplies with B equal to B, then U is equal to the one element, to element 1. And the third statement here says that if A here is a real number then A multiplies with 0 is equal to 0 element. Now I'm gonna give you the proof of A just to illustrate how we use the algebraic properties described earlier to prove this statement. Part A says that Z plus A is equal to A. And we want to show that Z here must be equal to the 0 element. So what do we do? The first step here, because the of these algebraic properties, we know there is a special element called minus A. And we're going to add minus A to both sides of this equation. So the first step here, we're using the first step. The axiom A form. Now, when you look at this equation, because of the associative property that we described earlier, then we can change the order of doing the addition. That is, instead of Z plus A first and then plus minus A, you can switch the order as follows. You do the addition between A and minus A first and then add it to Z. That is going back here. This is the second axiom A2. Now, because of the algebraic property of this special symbol minus A, we know A plus minus A is equal to the 0 element. That's why we have the third equation here. Z plus the 0 element equal to the 0 element. Going back to the set of properties of algebraic properties again, we see that by A3, by the third axiom here, A plus the 0 element is always equal to A. That's why here the left hand side of this equation is always equal to A. And the last equation here is exactly what we want to prove. So you see, this is an example of how you use algebraic properties to deduce a theorem about the set of real numbers. In this case, the theorem is about the uniqueness of the 0 element. The next theorem here says the following. If A is not equal to the 0 element and B is an element in the set of real numbers such that the multiplication of A and B is equal to the element 1, then B must be equal to 1 over A. So this is about the uniqueness of the reciprocal. Remember, 1 over A is a special symbol that satisfies certain properties. The theorem here says that if there is another number B that satisfies a special property, then it must be equal to that special symbol 1 over A. That's why this theorem is about the uniqueness of the reciprocal. Also, another statement of this theorem says that the multiplication of A and B equal to the zero element, then either A must be equal to 0 or B must be equal to the 0 element. I'm not going to give the proof of this theorem, but you can read about it more in the textbook. The takeaway point is that with these axioms and these theorems we just proved earlier, we just stated earlier, we can define other operation on the set of real numbers as well. So here we can define subtraction and similarly division. The important method is that using the algebraic properties described earlier, we can prove that these operations, subtraction and division, satisfy the usual properties of subtraction and division for concrete real numbers as we know them. So again, the summary is that first, let's forget about all these concrete real numbers that you are familiar with. Let's start from scratch. Let's start with a set of elements and you define two operations on these elements, namely addition and multiplication. These operations satisfy certain algebraic properties. Using these algebraic properties, you can show that these operations work in the same way as addition and multiplication for concrete real numbers. Now, the next topic is that using these algebraic properties, we can define rational and irrational numbers as follows. First, we start with a set of natural integers. How do we define the set of natural integers? We keep adding one together. That is, we're adding several copies of element 1 together. You have one copy of 1, that is the element 1. You have two copies, you add one copy of element 1 with another. Then you have another element denoted by this symbol, which we call 2. If we add another element 1 to that element, then we obtain another element called denoted by this symbol 3, and so on. That's how you define the set of all natural integers. Then the set of all integers is defined as follows. V gonna be the union of the set of natural integers n with the set consisting of element 0 and the set of negative of these natural integers. So minus n for any n inside the set of natural integers. That's how you define the set of all integers. Basically, the set of all integers consists of natural integers, then negatives and element 0. The set of rational numbers is defined as follows. It will consist of elements of the form B over A, with A, B are elements in the set of integers, and A here not equal to the 0 element. And a very important observation is that this set of all natural or all rational numbers here, Q here, actually satisfies all the few axioms that we mentioned earlier. And this is very, very interesting because we would like to set up a theory for real numbers. And now we see that if we just use just algebraic properties, then you cannot distinguish the set of real numbers from the set of all rational numbers, because Q, this set of rational numbers, satisfies all these algebraic properties as well. So the natural question is this set Q equal to the set of real number? In other words, does the set of all real numbers contain only rational numbers? The answer to this question is no, but it's going to take a while for us to see why it is the case. The first indicator is the following theorem, which says that there doesn't exist a rational number R such that the product of R with itself is equal to 2. So this is just an indicator, because at the moment we don't know if there is a real number satisfying this property. We just know that there doesn't exist a rational number satisfying this property. The proof is given in the note here for you to read at your leisure time. And that's it for today. We continue with some other properties of the real numbers next time.